Welcome back. This is Alex from the Four Sigmas, and today we're going to be doing the interference and diffraction experiment using the Pasco optics bench, light sensor, rotational motion sensor, red laser diode, all that good stuff that we showed you how to set up in our step-by-step tutorial on how to set it up. And so we're actually going to run the experiment using your favorite, Capstone. And a couple of things to consider, first of all, is that we're going to want our aperture with the single slits, in this case, about 11 centimeters in front of our red laser diode. And then we're going to want to maximize the distance between the aperture bracket with our light sensor and the aperture with the slits on it. And that's to reduce experimental error. Now, to record our data, the laser's going through the slit and it hits the aperture bracket, which is it's the name of the setup of the whole light sensor. And we're going to rotate the large ring, it looks like a flywheel, on top of the rotational motion sensor to, to bring the sensor along the diffraction and record our data. So I'm going to have Tony, I'm going to start recording our values here, and we're going to try to move it as smoothly as possible, but it doesn't matter if you stop, take a break, go get some coffee, because the sensor only records position, it doesn't record velocity, so as long as you're smooth, it will look really nice. And we're going to start it to the extreme right of the linear translator because that will give us positive values on our graph. Again, you could do it the other way, but it would look weird. We like positive values on our graphs. So I'm going to start recording now, and Tony's going to start moving it along the track. And we can see we've started to record values now. And we can see right here that we're getting to our central maximum. And it should be noted that this graph is the light intensity relative to the position on the track. And it looks like we're done, so we're going to stop recording now. And what we're going to do is we're going to record the positions of the first left and right minima relative to the central maximum. So I'm going to bring this scale out a little bit, and I'm going to bring our vertical scale up so we can more easily identify the actual point at the minimum of our graph. So how we're going to do this is we're going to take our coordinates tool and place it right over the bottom point in our first left minimum. And I'm going to go over here to my table. I already set it up for first left and right minimums. It takes a long time, and frankly, you guys don't have a lot of time in class to set up all these different tables for the different experiments you're going to do. So practically, you're just going to record these datas on a piece of paper and include it with your lab. So as we can see, the position of the first minima left of the central maximum is 0.0945 meters. So I'm going to record that. In my data table here, you would record it on your paper. And then I'm going to add another one, or you could just move your previous one over to the first minima right of the central maximum. And then we can see this is 0.2046 meters. And so these would be the values you would record on your piece of paper. Now I'm going to auto scale our graph again. And this would be the graph you would want to screenshot or save in your capstone file to include with your lab report. Because if you've ever taken a class with a scientist, scientists do love graphs and they get mad when you don't include graphs, especially a graph as pretty as this one. So that concludes our single slit tutorial. Now you're going to repeat this for the next 3 slit widths for the total of all 4. And in our next video, we'll cover how to do the double slit experiment. Thank you, and we'll see you in the next video. Wait a second.